as you want. But according to the mathematics that he discovered, Heisenberg discovered, he saw that the implication that you could measure the speed and the position both simultaneously and know them, and that they would check when you measure them again and again, was impossible. It was contrary to what the theory would predict. He claimed then that it would be like this, that if you measure the position very accurately and then tried to measure the speed, or the momentum, I should say more precisely, it's the speed times the mass, then if you measure the position again, it would be different. It would be possible to have something standing still, so if you measure the speed, measure the position again and again, it's always the same. But then, if you measured the momentum, even if it's supposed to come out zero, when you measure the position, it wouldn't be exactly the same. In other words, it's not like classical particles in a normal sense is possible only if you allow that measurements are going to disturb the system. That is, if you measure the position and then try to measure the momentum, then new position is irreversibly jiggled, if you want, by the momentum measurement. And then when you measure position, the momentum that you determined before is now screwed up. So if you measure the momentum again, it's not the same. It's completely analogous to our boxes. We measure, let's say, this and then that. We measure this. By pushing this button, it's always red. We're going to check it's perfect. We got a nice measurement of that. And now we try to measure this. Okay, we measure this and we see whether it's green, and we keep checking it's nice and green. Then we go back and see if this is still red. If it were red before, I forgot to say, let's suppose this were red. This is green. We look back, it might sometimes be green. In other words, it can change. This is a lot easier than positions, because positions can have all kinds of numerical values. Could be here or here or here or here, and here we have only two values, red or green. That's why this is kind of fun. It's easier to work with than numbers, which can have all kinds of values, and mathematics is more complicated. But here it's much easier. But you see then that the theory must predict that if you measure something, if you thought classically that there are these things under here that you're measuring, that this, whatever it is, this is the greeniness of this thing when you push 2, whatever it is, then you must allow that when you try to measure 1, you change whatever it is, the greeniness or redness for a 2 measurement. In other words, you can't measure 1 and then measure 2 and expect that it doesn't affect number 1, okay? And that's the general idea of the uncertainty principle, which more generalized says there are pairs of quantities such that if you measure 1, you cannot allow that you try to measure the other one. It doesn't change the first one, okay?
Irreversibly jiggled, is that what you said?
Yeah, that's what I said. I meant that was an informal way of saying it changes the value. You know, right, in a way that can't be undone, that's completely lost, that the information is now lost, or partially lost.
It's like shouting at your way.
Irreversibly undone.
You mean it's irreversible change that you...
It's a perturbation that you can't reverse.
It's true. It's true. Anyone who's married knows that all of the arguments that you've ever had through the entire married life come out in one great well on the next argument. Yeah.
The momentum has increased immensely.
Right.
Historical way that understanding the uncertainty
Yes.
came out, that there is too much of a focus on the jiggle, because there's a lot of systems at the atomic level where you only get one shot at them. You only get one measurement. What you do is you prepare a situation, and you, for instance, in a beam, you can say, I'm going to have half of them, I'm going to do position measurements, the other half momentum, and I only get one measurement.
That's right.
And the jiggle doesn't make any difference.
I know.
It says I can only, there's limitations on how I can prepare the system.
That's another way of speaking of it. The preparing means that you want to be able, it's a different idea, but it's the same idea. Suppose that I said that I have some way of setting it in. That's preparing it, so I know what their red or green are going to be. The answer is I can't set it in the way I want. This idea that I'm setting them in like this won't work. Even if you allow, I'm only allowed to push one button, I'm going to get in trouble in saying that I can set in particular numbers underneath. It's the same. You see, you're talking about predicting and preparing, but preparing is always done by, can be thought of as by measuring something else to get it right. It's another way of preparing. I could make sure that this is a red by pushing this button, checking that it's a red. If it's a green, I throw it out. I try it again until I get a red. Now I know I prepared it, so this is red. Now when I measure this, I change the preparation is screwed up. That's what preparation means.
Is this applicable only to single events, single particles, or is it applicable to massive numbers at once?
It's applicable to any system at all. The system may contain only one particle, or contain 3 particles, or 25 particles.
How about a billion particles?
It's perfectly all right. Numbers are no problem. Yes, it could be any number of particles.
Where you have beam collisions. You've got billions of particles.
This particular set of numbers with the 3/4 and the 1 was with 1 particle, and in this case with 2, and I had 2 boxes. And we're studying what happens with 2. The difficulties, the character of this thing is in the particle. And if you have a billion particles, each one or them are all doing the same kind of terrible thing, all right? So it's a universal difficulty. You're still disturbed. One of these guys that knows too much.
Okay. I'm not going to use the term Gerlach, I'm going to use your boxes.
Okay.
I could generate a situation in which I have boxes that are making themselves available for measurement.
Right, these. Let's forget the other box for a moment. These.
Yeah.
They keep
yeah.
coming out. Right.
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 Now I can create a situation
Right.
that certain combinations of that box have less probability of coming out.
What do you mean by certain combinations?
Those boxes in which
They're only the
okay,
red
I
ones.
can make it so that only 1/3 of the time you'll get red out of door number 1, and
Why don't
2/3 of the time.
Why don't we make it easy?
Green.
We always get red out of hole number 1. Does that satisfy?
No, the easy case is the trivial one. I'm trying to make the non-trivial.
What
case.
one?
And that is where I can put a bias on what the measurements are going
Yes.
to result
Right.
without ever having made a measurement.
Well, that may be whatever you say, whether you've made a measurement or not, but there is another way of putting a bias, is there? By just by checking what's in the box, and if it's right, sending it out. That's equivalent. It's equivalent because the forces which are making the separations are equivalent to.
But the point I'm trying to make is you don't have to do that.
Okay, yeah.
And if you don't do that, then you cannot.
What do you do, you see, and it's a little, we get into some complications as to how we do that with these boxes.
Certain kind of polarizing filters or filters over.
All right, yes, you can load the boxes with some particular prejudice, yes. But it's very much equivalent. Your filters are equivalent to my taking boxes and checking something about the, just a minute, checking something about the, I didn't say push a button, checking something about the boxes and letting them through if they were okay.
But that process is not one in which a measurement is made.
Whatever.
And that's the point I'm raising.
No,
is
it's
that-
not, it's the equivalent, it's equivalent. A measurement could have been made without any further
But
disturbance.
it's only when a measurement actually is made that you can attribute what happens to the fact that there was a jiggle took place. You're talking about the uncertainty relationship being due to the jiggle.
I have already got all of the difficulties with the other box. I don't need to take this other example. It doesn't add anything, okay? It doesn't add anything. So, a way of speaking would be to say, one of the things is either, I see what you want to say. I know what you're trying to say, which will make more clear when I take the case of 2 boxes. Let me just get to it in my own way, and then we'll come back. The original, one way of thinking about the uncertainty principle, which I made, which is less subtle than the regular way of describing it, was to say that if we tried to imagine that there was such a thing as the red, green, green, if we pushed a button on one of these things to determine it, it has to change the other one. And it's like that. If we imagine that a particle had a position and a momentum, then if we measure one, we have to disturb the other. Okay? In certain circumstances by luck, but not with position and momentum. No. If you measure position, you can have to disturb the momentum information.
But statistically, the disturbance.
That's what I'm talking about. So any prediction that you had made previously is not necessarily right. So your information is lost.
I think it would help the discussion if you tell how you measure position and how you measure momentum.
I don't have to, because I have an example where I'm measuring something else with buttons. I say you push the button and see whether the light's red or green. That's.
I'm talking about the electron.
I know, but I'm talking historically. The situation is I've tried to simplify this thing. If I went through the whole thing historically, we would go all through all the confusions and all of the difficulties that people have had for all these years to try to understand this clearly. So what I've tried to do is take a simpler example. And if I go back now and take all the confusing examples and go and explain all of those, I've made it much more complicated than it need be. What I'm telling you only about the history so you can find out what fits into what you just learned, what words belong to what. And what I'm trying to say is that the uncertainty principle is the statement that if you thought that you knew that you could say what was under here, that if you pushed a button, it's necessary that if you push another button, it changes that button. In other words, what's under here becomes uncertain, or is changed by in an uncertain way, because it's probabilistic, by pushing this other button. That's the idea. That's an example of the uncertainty principle. The uncertainty principle applied to this example, which we've been using as our primary example of the behavior of quantum mechanics. But the original statement of the uncertainty principle was more general and wasn't on this particular thing, and one of the examples was position and momentum measurements. We could go through the standard way of describing Heisenberg's uncertainty principle, but I think that we would only go much slower than if we went this way. Yes?
I just want to get clear on this. If you push the first button, you get red. You push the second button, you get green.
Right.
And then if you push the first button, you could get either red or green.
That's correct.
That would be the uncertainty principle.
That's right, it is.
If you,
Not only do you get it either red or green,
yeah.
but you get it red or green with a, if this were, let's say this was red, then this was green. You push this button, it's different than this button 3/4 of the time, the same 1/4 of the time. And that is always the same numbers, no matter what there was here before. You understand what I mean? The fact that what you've measured here before becomes irrelevant for future predictions after I push this button.
Like the roulette wheel situation. Yeah.
Something like that, yes. If you push this and it's red, or I don't care, green, whatever. Now you push this and it's green. Either way, the chance of this one being red or green is still, if this were green, 1/4 red, 3/4 green. Sorry. 1/4 green, 3/4 red. The fact it's 3/4 red, prejudice toward red, is not because it was red before, but because this one was green. For instance, if this were red and this accidentally were red when you pushed it, then this time, this is more likely to be green 3-to-1, 3 out of 4, than red 1 out of 4. Okay? But the proportions for this are completely independent of what your previous measurement was. So in this particular case, it's an example that measuring this means that any information you had about the other one before is completely irrelevant in future predictions. Okay? That's the nature of the...
I kept hearing you say when you push the second one, the first one would be the opposite.
No, I didn't mean to imply that. I meant only that it was opposite 3/4 of the time. In other words, it behaved exactly the same way, whether or not, what I really mean, and I made now clear, and thank you for your question, is that pressing the second one loses the information, any information that you had about pushing the first one. However, pushing the first one doesn't lose information if you want to measure the first one again directly without pushing any other one. Because if I measure it again, it always agrees, so I've got the information. So you say, nice, write it down. Now you push another one, I don't need to worry about what I had before. All future predictions of this one are independent of what I had before. Okay?
So memory is outside the system.
In this particular system. No, not outside the system, because if I push button 1, I have a memory. I can find out what it is again by pushing it again.
That's the only.
No, it isn't, because if I push button 2 and I knew that was red, then button 2 is got to be green 3 out of 4 times on the average.
But it doesn't know that.
But it happens.
You know.
No, I try it and it works.
That's what I mean.
Well, who knows what? I mean, the point is, no, it's a question of memory. That is to say, the system is behaving in a way that depended on what happened in the past. If this was red, and then I push this one, it's likely to be green 3 out of 4 times, and that is different than if this were green, so that it has a remembrance of what this was, if you want.
Memory is crazy.
What's true is that it doesn't remember 3 steps back. If you push a different button, it destroys the information from before, okay? So pushing 2 destroys the information you had from pushing 1. And that fact that has to happen, that if we had discovered, in other words, suppose that in the early days when this was first measured, you say there are different ways. I don't have to push the button. I can look inside the box by some kind of other trick. I got other methods. I scatter neutrons. I hokey pocus. I do something else to determine what this button would have been if I pushed it. After all, there are switches in there. After all, I can look at the way the thing is loaded before I push the button. That is, I make a different kind of measurement by a different method, which is to give me the same information. Now, if I could describe a different method which would have found out about these, which would not destroy those numbers, I never could get the 1/4 results that we were talking about. It's impossible. Well, Heisenberg's uncertainty principle went on to say, well, that not only does it change the measurement, but that no other way can exist to measure things that will disturb it less. There was a minimum amount of screw-up that you had to make when you measured button 2 about the information of 1. Okay. Now, this kind of a picture was a kind of a classical picture, and Heisenberg was talking about the relation of quantum mechanics to classical mechanics. Really, Heisenberg's principle can be looked at another way. There was old ideas of classical physics. Quantum mechanics is now different. It would be useful for people who are so used to classical physics to tell them when their ideas will fail. And his statement would be, another way of saying it would be, if you try to talk about something, so you simultaneously talk about the position and the momentum, you'll get in trouble. The logic will be wrong. Something will come out wrong. In the same way, in our case, if we start to say that we could say that behind here is a red thing, and behind here is a green, and behind here is a green, and that's what determines the things, and nothing changes, and they're definite, then we're going to get in trouble. The logic that we make after that is going to fail. So that's another way of saying it. So really, it's a statement of protection, a statement, so to speak, of where the new mechanics, that you might get away roughly with the old mechanics for large regions approximately, but you've got to watch out particularly if you're trying to talk about things which involve, in his case, position and momentum at the same time. And in our case, what's going to happen if I push this, and what's going to happen if I push that, simultaneously, without worrying about the fact that when I push one, it sort of changes the other. But this idea that there was something here which is being changed when I push the other button is still not satisfactory. That's what you wanted. Because we discover that we can make 2 boxes. And instead of finding out what's in here by piddling around in here, we remember one way was to push the button, the other way was to look underneath the switches or whatever. But whatever way we did it, it had to be true. Otherwise, we have an inconsistency that if we determine that this would have been red, and check it with the button, yes, it's red, check, yes. Let's take another. Suppose I found another way to look in here and look inside the switches, if there were any, and determine whether this was going to be red. All right, now if it's any good, after I've determined it was going to be red, then I can push the button and check whether it's true. Always works. But in the same way, I would get in trouble if after I determined that then I would get in some trouble with the chances. We know that. We know if we can determine this without changing these, we're going to get in trouble because we're not going to get the 3/4. But there is a nice way, so you could always say now with Heisenberg that any attempt to measure this by any method at all is going to affect it. And that's perfectly happy and satisfactory if you would say, well, that's very easy. I'll just imagine any piddling that you do in there inadvertently turns something in there. But there is a way, a magic way of determining what's here without touching this one. Just a different way, which is to measure this other box, which has been correlated with it that we talked about. We have this special circumstance that we can arrange things so that what this one gives can be determined by pushing that one. Now, because this box can be anywhere inside of cylindrical blockhouses or whatever else, it's a bit of a strain to suggest that when you push that, it changes this. And so we have this puzzle that we would like to say that when we determine what's in box number 1, we would have to change things in 2s and 3s if we took this old view that there is a potentiality that there are cards inside or something like that. So that the idea that there's cards inside or something like that, there's 2 ways of doing it. You can either say there's a marvelous force that exists at any distance instantaneously through blockhouses, through copper walls, through quartz. There's nothing you can do to affect it by doing something in between. Or simply to say that the old ideas are completely wet, that we can't talk logically about there being potentialities for red, green, and green, or for any other potentialities until we push the buttons. That to say what they might have been before we push them is no longer going to be permitted. We can't start to think. Well, let's see. In the beginning, it could have been that when I pushed whatever I set it in, when I set this in, I could say something like this. This is where all our trouble comes from. We say, let me see, I haven't pushed them yet, but there's various possibilities that when I push that, it would be red, that one green, and that one green, or that this one would be red, 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 or whatever. But these potentialities, physicists do not permit themselves to talk about anymore. They just say, after we push it, what it was, and don't try to talk about what it might have been if we had pushed it, if we haven't pushed it. In other words, the only things that can be described are things that have already been measured and not things that are potential.
There's always chicken in the icebox.
Perhaps there is. But you can't tell until you open the door. And opening the door may make the chicken disappear, or maybe not, with certain probabilities. But there's always chicken in the icebox. Now, whether that's true or not, we can't say that. In other words, even if we made up a theory that there was chicken in the icebox and we'd open a door, we get into difficulty because we can find another icebox by which you can determine whether the chicken's in there by opening its door. That's this one. And so you're really right about this chicken in the icebox door business. And so when the door's closed, we can't say whether there's chicken or not in the icebox. We try to say, I don't mean we can't say there's chicken or there's not chicken because we don't know. I mean the whole idea of saying it's either got chicken in it or it hasn't got chicken in it produces a failure.
The other one
It says
is
irreversibly jiggled.
No, you can't use that anymore. You can't say that it is either one way or the other, and when you open the icebox it changes, because we can find out what was in the icebox by another measurement, and that gets inconsistent. Yes. So
The old game of trying to figure out if the light is on when the door is closed on.
it's gotten worse. You see, because with the old thing, the question is whether the light is on or the light is off when the door is closed. It seems legitimate to say the following. Either the light is on or it's off. There are two possibilities. Now let me start thinking, okay? The beginning step is no longer allowed. Before we push the button, we can't say, if we do, we're going to get into logical troubles and not be able to understand how nature works. So we have to train ourselves, and that's what physicists have done. They train themselves in a negative fashion to be very careful, not to say things like, well, let's see. This is either red, green, green, what would happen if I push the buttons, or else it's green, green, red, or else and so forth. Those are possibilities. Now I'll push the button to see what I get. The whole statement that these are the list of possibilities is no longer permitted. So you have to be very careful with the logic, okay? And what I'm going to show you in the next days is what kind of machinery we actually do use and what kind of thinking we actually do use in order to predict results like this, because we can predict them, you see. We do have a theory for all this. It's not that chaotic, but it's not at all like what you're used to. Simple ideas of logic, the simplest idea that these are the possibilities, and let's see which one it is not permitted. You get into trouble. What is permitted and how you can do it so you don't get into trouble will be described in future workshop sessions. Okay. Now, but now I'm trying to explain to you why I claimed in my workshop advertisement that I would tell you about the uncertainty principle and Bell's theorem and Einstein-Podolsky paradox, because I have just done so. It's all finished. But you will not be satisfied because you don't know where each of the pieces are. So first I told you where the uncertainty principle was, the statement that by measuring something you've got to disturb the predicted expectation for something else. But it's more subtle. You're not allowed to have an expected prediction for something else anymore and say it's changed. You have to have it be more abstract in order to be able to understand this situation. There, of course, is another way, and people have proposed it, and that is to say that when you push this, there's a marvelous influence that spreads instantaneously through all the world and changes those other things which were correlated that you expect to measure, okay? This is possible, and that's a model that you might prefer over the idea of saying that there's no such, you can't talk about the possibilities before you make the measurements. That has turned out people have tried to do that, there are two directions in which you can go. You can say, yeah, there's always this instantaneous action, and it does exactly the right thing, and it doesn't depend on the distance. But that's an unnecessary complication, so to speak. I mean, it doesn't help any. It's perfectly okay, but since an action can go at any distance without any effect, there's no laws about it, except that it does just exactly what you want. So just describe what you want, and never mind saying that it's done by some special law or some special magic, because that special high-speed interaction is only to protect your prejudices about the way you like to think about things. That's all it was for. It didn't change any results of what you'd expect for any experiment, which is what physics is about. And so, don't bother to say it. It doesn't make any difference. If you want, you say, this is so puzzling, I'd like to say there's an instantaneous action that goes at infinite speed everywhere and is not affected by anything, only to make the answers come out right. Okay? Is okay. Well, you want to, okay, but it doesn't make any difference, right? Because the answers come out the same. So, yeah, so we just don't bother with saying it, most physicists. Now, however, there's another possibility, and that is that there really is such an action, but it isn't, as I said, that for short distances it's independent of distance, but for long distances it disappears, that it takes a little bit of time, that it does something. Then the predictions will be changed. For instance, if these boxes are pulled further apart, then this will not agree with that anymore. Or if I measure this too quickly or not quickly enough, early enough, I can't predict what that one's going to be, and so on, because there's the delays and there's character to the interaction. As soon as the interaction has character, other than this universal marvel that goes at all distances, at all speeds, instantaneously, just to get the right answer, but it's more complicated. You say it takes time to go, or it weakens with distance, or anything like that. It makes new predictions. So, in the earlier, some people, early on, not many, but some, proposed just that. They couldn't take it. And so you said there must be an interaction. Position again, it would be different. It would be possible to have something standing still, so if you measure the speed, measure the position again and again, it's always the same. But then, if you measured the momentum, even if it's supposed to come out zero, when you measure the position, it wouldn't be exactly the same. In other words, it's not like classical particles in a normal sense is possible only if you allow that measurements are going to disturb the system. That is, if you measure the position and then try to measure the momentum, then nice and green. Then we go back and see if this is still red. If it were red before, I forgot to say, let's suppose this were red. This is green. We look back, it might sometimes be green. In other words, it can change. This is a lot easier than positions, because positions can have all kinds of numerical values. Could be here or here or here or here, and here we have only two values, red or green. That's why this is kind of fun. It's easier to work with than numbers, which can have all kinds of values, and mathematics is more complicated. But here it's much easier. But you see then that the theory must predict that if you measure something, if you thought classically that there are these things under here that you're measuring, that this, whatever it is, this is the greeniness of this thing when you push 2, whatever it is, then you must allow that when you try to measure 1, you change whatever it is, the greeniness or redness for a 2 measurement. In other words, you can't measure 1 and then measure 2 and expect that it doesn't affect number 1, okay? And that's the general idea of the uncertainty principle, which more generalized says there are as you want. But according to the mathematics that he discovered, Heisenberg discovered, he saw that the implication that you could measure the speed and the position both simultaneously and know them, and that they would check when you measure them again and again, was impossible. It was contra to what the theory would predict. He claimed then that it would be like this, that if you measure the position very accurately and then tried to measure the speed, or the momentum, I should say more precisely, it's the speed times the mass, then if you measure the position is irreversibly jiggled, if you want, by the momentum measurement. And then when you measure position, the momentum that you determined before is now screwed up. So if you measure the momentum again, it's not the same. It's completely analogous to our boxes. We measure, let's say, this and then that. We measure this, by pushing this button, it's always red. We're going to check it's perfect. We got a nice measurement of that. And now we try to measure this. Okay, we measure this and we see whether it's green, and we keep checking this.